KCBS, in partnership with UCSF Health, presents As Prescribed, a weekly conversation with leading medical experts from UCSF Medical Center and UCSF Benioff Children's Hospitals.
Hello and welcome to As Prescribed. I'm Kathy Novak. Today we are talking about a new advance in technology that could allow people who have lost the ability to speak to get their voices back, or at least a more natural way to communicate. Here to explain more is Dr. Edward Chang. He's the chair of the Department of Neurological Surgery at UCSF and senior author of this study, which has just been published in the New England Journal of Medicine. Dr. Chang, thanks so much for joining us.
Hi, Kathy. Thanks for allowing me to participate.
So, Dr. Chang, tell us how the study worked.
Sure. This study is really a proof of principle. It's the first time we've been able to translate brain signals from someone who had a stroke 15 years ago in the part of the brain called the brainstem that left him paralyzed in the arms and legs, and also with a condition called anarthria, where he's unable to speak. And he participated in this particular clinical trial where we translated the neural activity from his brain, from his brain that controls the areas of the vocal tract, like the lips, the jaw, and the tongue, to words. So we were able to translate the brain waves associated with words into actual words and text in order to help restore some of his communication.
And when we're talking about giving someone who has lost the ability to speak a way to communicate, my mind goes to the machine that Stephen Hawking used. Can you talk a little bit about how this is different?
Yeah, I'd love to. A lot of us, when we've seen that video with Stephen Hawking's, it's actually really not him speaking in real time. It's actually his text that's being read out by a computer and using speech synthesis to read out something that's already been perhaps pre-recorded or pre-written. In this particular study, what we're trying to do is restore someone's ability to communicate in real time as he is trying to speak. So not necessarily reading out pre-prepared text, but actually just translating that brain activity that's supposed to be going to the vocal tract to a machine that interprets that and puts it into words as text.
So, for example, you could study what his brain does when he thinks about the word water and then ask if he's thirsty?
Actually, yeah. So it's close to that, but it's not really what he's feeling or thinking, but what he's actually trying to say. And so the way that the technology that we've been working on works is it's tapping into the parts of the brain that are involved with the muscles and the control of the muscles for the vocal tract. So it's more like the patterns that govern the movements of our vocal tract when we speak. So it's not really about the meaning or our feelings or anything. It's really about what we're actually trying to get our mouth to say.
So does that also mean then that this technology ultimately would not be able to read someone's thoughts and then say them out loud when they don't want that shared?
No, this is really just about like, what are you actually trying to say and attempting to say and trying to get your mouth to produce his words. Again, for someone who's been paralyzed and can't get that communicated.
So if this is then the first demonstration of direct decoding of full words from brain activity into text, where do you see this going to from here?
Well, I think we're really just at the beginning. Like I said at the start, this is a proof of principle. This is the first person we worked with in this particular trial. And it was really the first part of a long set of studies that we want to be able to make it faster with a much larger vocabulary. In the future someday to be able to use this across different languages. But we're really just at the starting point of this and very excited by what we see, but there is such a long road ahead as well.
What would you need to do to be able to adapt this to other languages?
Well, part of this we think is fairly shared. The strategy for the technology is in what brain areas are encoding speech are largely the same across different brain areas, and we can use that knowledge that we have in order to help with this a lot. But the nuances, the syntax, the grammar, the meaning of all the words in a given language actually have to be tuned and programmed into the technology that we develop. So every person, in fact, may have to have something specifically tailored for this technology to work. And I think that's only natural because we all have, very specific ways of speaking with accents and way of pronouncing words, etc., beyond just the very big differences between different languages.
And in order to do this study, you used a lot of technology that we may be familiar with in our everyday life, right? Autocorrect, predictive texting, that sort of thing?
Yeah, that's exactly right. So the algorithms, the machine learning algorithms that we use to translate those brainwaves into words is very, very powerful, but it's not perfect. In fact, far from perfect. And there's still a lot of errors. So what we've been able to borrow from speech technology, essentially what we call language models or natural language processing, like predictive text or autocorrect features, are something that have been very, very helpful for this project. So if the wrong word is decoded, it can get corrected on the fly, and that improves the accuracy and speed of the whole technology.
And how could this be then transformational if you're taking it from the use of tools that exist now that involve texts, as you described in the case of Stephen Hawking, where they were pre-prepared, to be able to actually read brain signals and speak ultimately in a more conversational way?
Yeah, well, I think that that's definitely our long-term goal, which is to try to restore the very unique and special behavior of human speech. And as humans, we can communicate information really rapidly, just like you and I are going back and forth at the rate of 120 to 150 words per minute. Allows us as humans to convey information very quickly. And that's one of the biggest frustrations for people who have speech disabilities, which is communicating that information quickly is almost impossible. So we're taking that very seriously and thinking about how to make that as our next big priority.
So without the ability to speak to you, have you been able to gauge the reaction from the person who's participating in this study to see his brainwaves being translated into a real word?
Oh, absolutely. I mean, I think that that's been one of the most fulfilling and satisfying aspects of this entire project. We go into this hoping for the best, but really at the same time acknowledging that it could be, futile. And so we're very, very pleased with where we are right now. The participant who's been involved with our study is an incredible person, but I have to say it takes a lot of work on both sides, and starting something new like this for the first time is very challenging. And so I give a lot of credit to the participant in the study, as well as all the brilliant students and engineers in the lab that made it happen.
Well, it's absolutely fascinating. Dr. Edward Chang, thanks so much for your time.
Thanks, Kathy.
Dr. Edward Chang is chair of the Department of Neurological Surgery at UCSF, and I'm Kathy Novak. Thanks so much for tuning in to As Prescribed.
As Prescribed, every Thursday at 1:30, right here on the Bay Area's news station, All News 106.9 and AM 740 KCBS, and streaming on the Odyssey app. The proceeding was sponsored by UCSF.